We're studying analysis from book Rudin. We are on chapter 2, finite, countable, and uncountable sets. So let's go over introduction. We start by defining a mapping, the domain, and range. Suppose we have two sets. Let A and B are two sets. A mapping from A to B is actually a rule that takes values from A and assign them to values in set B. So suppose to each element X in A, it is assigned to a value f of x in B by mapping or function f. A is called the domain of the function, and B in general is called the codomain. The set of all values f of x is called the range of function f. Well, what if you have subsets? Let E be a subset of A. And suppose you're taking the function f, mapping A into B. F of E is the set of all y values or f of x such that x belongs to set E. F of E is called the image of E under function f. Now suppose you take a subset from B. Now let E be a subset of B. The notation that we use for the image of B under F has a little bit of change with -1 as the exponent, but it's not actually 1 over F. We call it the inverse image of set E is the set of all x values such that f of x belongs to B. So this new set is called the inverse image of E under function f. So far we defined the image of E under function f and the inverse image of E under f. So E, in this case, is a subset of A, and in the second case, inverse image is a subset of B, the codomain. Note that if inverse image of E has at most one element, then we say that our function is a one-to-one function or injective function. Is one-to-one or injective. More officially, we can say that for function f that maps A to B, f is one-to-one, provided that y values are different from each other whenever x values are distinct from each other. So x1 is different from x2, it results in f of x1 different from f of x2. Another note. So if for function f that maps A to B, the image of the domain is exactly the same as codomain B. So if the image of the domain under F is equal to codomain, we say that it is onto or surging. If a function is one-to-one and onto, or when it's injective and surjective, it means that we have a one-to-one correspondence between two sets. So let's write this as an official definition. If there is a one-to-one mapping from A onto B. So note that we're using, instead of into, we're using onto B. It means that we are working with a one-to-one surjective function. So onto surjective, or f of A, is equal to. So if there is a one-to-one mapping from A onto B, we say that there is a one-to-one correspondence between A and B. We also say that in this case, we say that A and B are equivalent. The symbol that we use is A is equivalent to B. What's the meaning of that? It means that the relation between A and B is reflexive. It means that A is equivalent to A. It is symmetric. It means that if A is equivalent to B, then we can conclude that B is also equivalent to A. And finally, it's transitive. What's the meaning of that? It means that if A is equivalent to set B and set B is equivalent to set C, for sure we can say that A is equivalent to set C. So if we can find a one-to-one mapping between A and A, remember that in this case we can work with the identity function. We have a reflexive relation. If A is equivalent to B, it means that if we have a function, one-to-one correspondence between A and B, then we can find a one-to-one correspondence between B and A. We have symmetric relation. If we have a one-to-one correspondence between A and B, and also if we have another one-to-one correspondence relation function between B and C, then for sure you can find a one-to-one correspondence between A and C. That's the meaning of that. Or we say that A and B are equivalent to each other. More definition for you. Now we're going to talk about finite, countable, infinite, uncountable sets. So for any positive integer like n, J sub n is the set of 1, 2, 3, up to n. So J sub n is positive integers up to n. And let J be the set of all positive integers. So J consists of 1, 2, 3, 4, and so on. Suppose you have a set. Let A be any set. We say that A is finite if we can find a one-to-one correspondence between A and J sub n. B, we say that A is infinite if A is not finite. C, we say that A is countable if A has a one-to-one correspondence between with J and D, A is at most countable if it's either finite or countable. Example. Well, in this example, we have A as the set of all integers. What is our claim? Our claim is that A is countable. So how do we prove that? How do we show that A is a countable set? Well, to show that A is countable, we need to show that A has a one-to-one correspondence to set J. What is set J? J is the set of all positive integers. So to show that A is countable, you need to find a one-to-one correspondence or a one-to-one and surjective function that maps A to J. Or another word, they are equivalent to each other. We can define many functions, many one-to-one correspondence. One of them is defined this way. F of n can be defined this way. If n is an even number, I'm going to define the function to be n divided by 2. So this way, if n is even, I get all numbers, positive numbers, 1, 2, 3, 4, 5, 6, so it counts all positive numbers for me. If n is odd, I'm going to define it this way. Negative, I'm going to use a negative sign. I created all the positive numbers. Now I'm moving on to define negative numbers. N minus 1 divided by 2. If n is odd, then I get all negative values. This is a one-to-one function, and it is surjective or anti. So since we have a one-to-one correspondence, it means that we can connect A to J. A is equivalent to J. By using the definition, A is countable. Since F is a one-to-one correspondence, it means that A is equivalent to J. So by definition, A is countable. Let's define a sequence. When we're talking about a sequence, you're actually talking about a function with a specific domain. So a sequence is a function with domain J. What is J? J is positive integers. We usually denote a sequence by its terms. We define the sequence as f of n, or using its general term, x sub n. The terms of a sequence is denoted by x sub 1, x sub 2, x sub 3, and so on. Sometimes we can use x sub 0, x sub 1, x sub 2, x sub 3, and the rest of the terms of a sequence.